Our first speaker today will be Chad Nestor from the Tallinn University of Technology, and he's going to be talking about partial and relational algebraic theories. Whenever you want.
All right, thanks. So yes, as he says, my name is Chad Nestor. I'm a PhD student at Tallinn University of Technology, supervised by Pavel Sobczynski. And today I'm going to tell you about some work we've been doing on partial and relational algebraic theories as a generalization of sort of normal algebraic theories. And so the plan for the talk is that there are three parts. One is sort of a recap of algebraic theories from our viewpoint, then we'll do partial algebraic theories, and then we'll do relational algebraic theories. Each of these three parts has two parts. In the first one, we'll do sort of syntax for this notion of algebraic theory, and all of these are going to be sort of string diagrammatic syntax. That's sort of one of the cool things that about this, is that we get nice syntax by using string diagrams. And then the second part will be about semantics, so categories of models and model morphisms and what they are. So to start off, as you may know, categories with finite products are the same thing as symmetric monoidal categories, where at every object we have both a copying operation, pictured here on the left on the first line, that satisfies this sort of copying equation, saying that if I do f to something and then copy the output, that's the same as copying the input and doing f to each copy. And also we have a deleting operation, sort of pictured here as a string diagram below on the left, and that satisfies this sort of deleting equation that says if I do f to something and then delete the output, I may as well have just deleted that thing in the first place. And so to be a category with products, this sort of structure is required to form a commutative comonoid, so just in the normal way expressed with string diagrams there, and has to satisfy some sensible coherence conditions with respect to the monoidal structure. And so that's sort of categories with products, syntax for string diagrammatically. And we're going to define well, it's just how you define it. An algebraic theory is just a category with finite products. And then a model of an algebraic theory is a functor from that category into the category of sets and total functions that preserves finite products. So sort of preserves the copying and deletion. And so, for example, we get things out like, well, the models of the theory of commutative monoids as a category are exactly the commutative monoids. So we'll look at the theory of commutative monoids now. I've displayed it here both in the usual sort of algebraic theory syntax and the string diagrammatic syntax to give you an idea of the comparison. So for commutative monoids, we have two generators. One corresponding to the binary operation is pictured here on the left in both the classical syntax, sort of on the left, and as a generator for our string diagrams on the right on the left. And then we have, of course, the monoidal unit, which is an operator with no arguments, pictured here as a string diagram from sort of the monoidal unit into whatever the carrier is. And we ask that this satisfies some equations. In particular, we ask that the binary operation is associative and commutative and unital. So, associativity here, we ask that if I apply x1, which we imagine coming in on the first wire, to x2 on the second wire, and then apply that to x3, well, that's the same as doing that in the other order. You know all this, but it helps to get the connection between the classical syntax and the diagrams. And so, what the copying and deleting allow us to do is both to use variables multiple times in the same term and also to not use variables in a term, which we might do a bit later. So for example, if I wanted to have the term x1 applied to x2 applied to x1, noting here that the x1 here and the x1 here are the same thing, then what I have to do is sort of, I imagine x1 coming in on the first wire and x2 coming in on the second wire. Then I make two copies of x1, I apply one of them to x2, and I apply the result of that to x1, and then the term on the left here is sort of coming out on the bottom wire. And so similarly, I could just do x1 applied to x2 with the generator for the binary operation. And substitution. Substitution in sort of algebraic theories, how you compose terms in the usual setup is you substitute. So if I had x1 applied to x2 applied to x1, so this term, and in that term, I wanted to substitute the monoidal unit E for x1, and I wanted to substitute x1 applied to x2 for x2, then I could do that string diagrammatically by writing sort of the term I want to substitute things into on the bottom. So here I've written x1 applied to x2 applied to x1. The term up here is the same as the bottom of this diagram here. And then the thing I want to substitute for x1, I put on the first wire. I sort of stick it on top. And similarly, the thing I want to substitute for x2, I stick on the second wire. And then our equations tell us that this string diagram is equivalent to this other string diagram, which turns out to correspond to the result of substituting those things for those variables in that term. So and this is how we get classical syntax string diagrammatically, or we can use string diagrams instead. And the correspondence is quite strong. And as you may know, once I have algebraic theories, a model morphism, so a model, remember, is a functor that preserves finite products from this category into sets. And a model morphism is just a natural transformation. And it turns out that these capture sort of homomorphisms very well. So for the theory of commutative monoids, for example, the model morphisms are exactly the monoid homomorphisms, which is what you would want. And in this way, the models and the model morphisms always form a category for any algebraic theory, and we call categories that you can get this way varieties. So that was sort of the summary of classical algebraic theories. I've promised to tell you about partial and relational algebraic theories, and so we can ask questions like, what if I want algebraic theories, but whose operations correspond to partial functions on sets instead of total functions on sets? So I want my models in the category of partial functions on sets, not in the category of total functions on sets. And something we can sort of say right away is that because classical syntax corresponds so strongly to finite product structure, and partial functions on sets doesn't have finite product structure, we probably can't use classical syntax. We're going to need to use something else. And the something else we're going to use is sort of the analogous structure that par does have. And so it turns out that we still have a copying operation at every object, just like before, and it satisfies that copying equation. In addition, we have a restriction thing at every object, and it looks a lot like deletion, but it doesn't satisfy the deletion equation. That's just not true here. We're not going to insist that it holds. And finally, I have a sameness operation at every object that it works like a partial equality test. So you imagine it in partial functions and sets. It's the partial function that takes in two things, and if they are the same thing, returns that thing, but otherwise is undefined. This structure will require that copying and restriction form a commutative comonoid, just like before. We'll ask that sameness is commutative and dissociative, and that copying and sameness satisfy these special Frobenius axioms, along with some coherence with respect to the monoidal structure. And so par has this, and this will be our notion of partial algebraic theory. I guess before we move on, it's worth talking about how we can use the restriction generator to talk about the domain of definition of something and capture the partiality, or say that something is total or partial. And the way it works is that the domain of definition of f corresponds to this arrow from its domain into the monoidal unit, sort of f followed by the restriction. And so I can insist that f is defined exactly when g is defined by asking that f restriction is equal to g restriction, sort of like here. And we're going to use that. And so now we'll take these categories, the symmetric monoidal categories with this sort of non-unital Frobenius algebra structure, as our notion of partial algebraic theory. For those in the know, this is exactly the same thing as a discrete Cartesian restriction category from the work of Robin Cockett, Peter Hofstra, and Zhujiang Guo, but we're gonna call them partial algebraic theories for now. And our notion of model will again be a symmetric monoidal functor from the partial theory into sets and partial functions this time that preserves the copying and the restriction and the sameness, which makes sense because par has all of that. And the notion of model morphism is a bit different. Instead of being a natural transformation between the sort of functors that are the models, it's a Lax transformation. A Lax transformation is just a natural transformation, except that the naturality square commutes up to an inequality. In this case, the inequality is the extension ordering on partial functions. So it says that if f of f composed with alpha at y is defined, then so is alpha at x composed with g of f, and they are equal. But they're not the same function because alpha at x, g of f might be defined on some inputs that f of f, alpha at y is not defined on. And so that's our notion of Lax transformation. And it turns out to be a good notion of model morphism, as we'll see. So, for example, an example of a partial theory is the theory of separation algebras. So a separation algebra is a partial commutative monoid that is cancellative. So we need, well, a partial binary operation representing, the monoid operation. That's this generator here. We'll need a unit for our partial monoid. That's this generator here. The unit generator has to be total so that it actually defines a point in the carrier. That's what this turns out to mean. The partial binary operation must, of course, be associative and commutative. And here we've asked for it to be left unital. So that's all very straightforward. That's a partial monoid. And here we can express cancellativity using the sameness operator. So if we sort of read this as a term, so x1 is coming in on the first wire, x2 on the second wire, and x3 on the third wire, it says that sort of the situation in which x1, where we get it in and we make two copies of it, and so we have x1 applied to x2, and over here we have x2 applied to x3, and those are the same. So x1 applied to x2 is x2, or x1 applied to x3. Well, that's the same as the situation in which x2 is equal to x3. And this is one way to express cancellativity. And so sure enough, models of this theory are separation algebras. Model morphisms happen to be sort of partial monoid morphisms. The right notion of partial monoid morphism is a total function from one carrier to another, such that if sort of we see on the left here, and when we treat this inequality as an implication, that if f of a applied to b is defined, then f of a applied to f of b is also defined and they're equal. It's not a by implication because that's not how it works. Another example of the sort of thing we can do with partial algebraic theories is the theory of categories. So this time we're going to have a two-sorted theory. So we have a sort or an object in our category A for arrows and a sort O for objects. We have source and target maps that send an arrow to its domain and codomain respectively, a map ID that takes an object to the identity arrow on it, and a partial operation on arrows, partial binary operation corresponding to composition. So we deal with the domains of definition with these axioms here in the upper right. They say that the source, target, and identity, or ID, maps are all total, and that the composition operation is defined exactly when the source of the second arrow is equal to the target of the first. And then the unit laws are expressed and the domain of the identities are expressed by the equations below. So sure enough, models of this are small categories. Model morphisms are precisely functors. So that's pretty cool. There is a variety theorem that we've proven. This part is joint work with Pavel Sobocinski, Ivan Liberti, and Fosco Loredjan. And the variety theorem is that the categories that arise as models and model morphisms of partial theories are precisely the locally finitely presentable categories. We're not going to talk about what those are, but this is a good theorem. And as a corollary, we get Morita equivalence, a characterization of. So it turns out that two partial theories present the same locally finitely presentable category if and only if splitting a class of idempotents called restriction idempotents in both of the theories yields equivalent categories. It turns out it's actually enough to just split the idempotents, but that's not published yet, so don't tell anyone. All right, so that's partial theories, fast. We'll move on to the final part of the talk where we talk about relational algebraic theories. We're going to ask the same question. What if I want models of my algebraic theories in the category of sets and relations instead of the category of sets and functions? We've heard this before. Once again, we can't use classical syntax. It won't work. Instead, we have to use string diagrams, or we don't have to, but we're going to. The structure that REL has, kind of in the vein of the structure we've seen that par and set have, is the structure of a Cartesian bicategory of relations. So what that means is that there's a morphism from X to X tensor X, corresponding to the relation, the sort of diagonal relation that relates A to, well, A and A. And then we have a morphism from X tensor X to X that's the sort of the converse of that, the codiagonal relation. Similarly, we have a relation epsilon from X to the monoidal unit that relates just everything in X to the one element of this set. The I here is the one element set in REL. And we have the converse of that, this eta thing. And this structure forms in REL and will be required for us to form a special commutative Frobenius algebra at every object. So that means that delta and epsilon are a commutative comonoid, mu and eta are a commutative monoid, delta and mu together satisfy the special Frobenius equations. And it turns out, sort of a lemma here, it turns out that it's enough to get this Cartesian bicategory of relation structure to just say that we don't care how many times a thing is related to another thing. We don't care about multiplicity. So if I have delta f tensor f mu, that's just the same thing as f. And so we'll call a symmetric monodal category with this structure a relational algebraic theory, noting once more that this is the same thing as a Cartesian bicategory of relations. Then, like before, a model will be a symmetric monoidal functor from the theory into sets and relations that preserves this Frobenius algebra structure. Once again, this makes sense because REL has that structure. And model morphisms are, again, Lax transformations, same definition. So what can we do with this? One example that's kind of illustrative is that we can do a relational theory of non-empty sets. And so we take it to have sort of one generating object, the category. It has no generating morphisms, aside from the structural ones for a relational theory. And we impose the equation that the unit followed by the co-unit is the identity morphism on the monoidal unit. And this turns out to be the same thing as asking that the carrier, so if you have a model, that the carrier of that model is a non-empty set. This is because relational composition involves existential quantification or pullback. And so we're sort of asking for the set of all, I'm tripping a little bit, but what it turns out to say, and you can work it out, is that the carrier is non-empty. And then model morphisms are just functions. You can contrast this, total functions, you can contrast this to the category of pointed sets, for example, where morphisms of pointed sets have to preserve the point. Here we have sets with something in them, but that something doesn't have to be preserved by the morphisms. So this is kind of neat. In a similar vein, we can sort of do a theory of regular semigroups, so notably not a partial theory. And the theory of regular semigroups has one generating morphism and one generating object corresponding to the carrier of the semigroup. So we'll draw the binary operation of the semigroup like this here on the left. We insist that it's a function. So this sort of says that it's a deterministic relation here. And this says that it's a total deterministic relation, so a function. We ask that it's associative as a binary operation. We ask that it satisfies the axiom of regularity. So the normal way you write that is that for all a in the carrier, there is some x in the carrier such that a applied to x applied to a is equal to a. And so for us, what that looks like is, well, the A is coming in on the first wire here. We're saying that, well, if I sort of make a copy of A and I get, this is like saying, there exists something, and the thing that exists comes in on the wire below the unit. So we're saying, all right, well, there is some x such that when I apply A to x and apply the result to A, that gives me the same thing out at the bottom as just doing nothing, which is A. So I can capture the axiom of regularity using these relational algebraic theories. There's a variety theorem for this notion of theory as well. The categories that arise as models and model morphisms are precisely the definable categories. We're not going to talk about that, but they're a thing. I would like to know more about them. I don't understand them very well. It's a sort of a recent notion. We also get Morita equivalence as a corollary. Two relational theories present the same definable category if and only if splitting their symmetric idempotence yields equivalent categories, which is exciting because that's another way of saying, symmetric idempotence are the same thing as partial equivalence relations. And I think maybe this explains why partial equivalence relations show up all the time in categorical logic, but we'll see. And that's the end of my talk. This is based on 3 papers, one published, 2 not. The first is called Functorial Semantics for Partial Theories with Ivan Dilberti, Fausto Lovajan, and Pavel Sobocinski in Popple this year. And there are 2 more you see here about functorial semantics for relational theories and one about the variety theorem for that notion of theory that you can find on the archive if you're interested. I'll pause for questions soon, but before I do stop for questions, just let me explain this big diagram. This is a commutative diagram of left 2 adjoints, explaining the sort of, how does all this work technically? How did you prove the variety theorems? It's all in this diagram. So every arrow is the left adjoint of an adjunction, if that adjunction, of 2 categories, sorry. If that adjunction is an equivalence of 2 categories, there's a little squiggle next to the arrow. Anything that is a solid arrow is established fact. Anything that is a dashed arrow is something that I think is true and that will commute, but I haven't proven it yet. And that's the end of my talk. Thank you very much for listening.
Thank you very much, Chad.